Hello, and welcome to Nicoya's third episode of our OpenSPR Pro Tips series. My name is Mike Piazza, and I am a customer success scientist here at Nicoya. We appreciate you joining us today, and we really hope that you're all staying safe and are doing well during this pretty challenging time. And again, hopefully today a little science can take our mind off things that are going on outside and get us focusing back on the science that we hope to all be doing soon back in our labs. So for today's webinar, what we're going to be doing is we're going to be getting re-familiar with how to use the instrument if you haven't been on it in a while, or as a bit of a training refresher for those new to using it and new students that are going to be using it in your lab. So what we're going to do is we're going to do a full test setup on the instrument. We're going to go through all the protocols necessary for getting a sensor loaded, proper sample loading and sample injections, and what an outline of a validation test would look like to ensure that the instrument is running optimally. So for that to transpire, what we're going to do is I'm going to go through all the items that would be necessary for getting up to speed with the instrument. So for today's test, we're going to be just running simple glucose injections, so simple 25 mg per mil, standard what we would do in a training test run with your lab group. We also require some 80% isopropanol for cleaning the flow cell and our bubble removal steps. We're going to be using water as our running buffer today, so we'll require some water in a separate container that we can use to clean out the sample loop. For today's test, we're going to be using the diagnostic sensors. So these would have come in the accessories kit that you have. They're just titled diagnostic sensors. We use them for running diagnostic experiments on the instrument. We'll also require some gloves. We'll always be wearing gloves while doing these tests. A set of tweezers for getting our sensor out of the sensor container. Some lint-free wipes. If you don't have lint-free wipes, you can use Kim wipes. For today's test, we will be using, again, water as our running buffer and glucose as our analyte solution. So we'll require syringes for each one of our unique solvents we're going to be using. We also have some squirt bottle water and a little waste beaker to rinse out our new sensor. And in this case, we're just going to use a little hand pump. In your accessories box, it would be the blue small hand pump that comes with your instrument. Next thing we need to do is ensure that the bottles we're going to be using for today's test are connected to the instrument. So the first thing we can do is ensure that our waste bottle in the back has all three of our waste lines going into it. Now, in this test today, we are going to be using our 2-channel instrument. So everything we are doing today can be set up a test on the OpenSPR XT also. In your situation, you'll probably have 2 lines going into that waste bottle. Next, we're going to ensure that our bottle labeled water line is filled with water. And then since our running buffer for today going through bottle 1 is water, we're going to make sure that that's also filled with water. Now, one thing to note when inserting the lines into the bottle and using our screws to tighten them, we want to make sure that we do not over tighten the screws on these caps, as that could lead to the tubes being pinched and causing cloggage in our instrument. So we basically want to tighten it to the point where the tube can still move with some force, but is pretty sturdy in there. And then you can just tuck the bottle away into the side of the instrument there. So with respect to the instrument itself, once the USB is connected to the laptop that you're using to run the software, to turn the instrument on, we will use the power button in the bottom right. If we ever had to turn it off manually, we would hold that button down for 5 seconds to ensure that the instrument has been shut off. The other section we're going to use in the front of the instrument is our injection port here. So here is where we're going to be introducing all of our samples to the sensor and the flow cell area through the injection port there. Now again, if you're using the XT in your lab, this port would not be connected to your instrument. You would just have a couple of lines that are going to the auto sampler tray, and you would just put your samples in a 96 well plate. So what we're going to do now is we're going to shift over to the software itself. So what we have shown here is what the software looks like after we've started tests. So in this situation, we connected via the home screen, we clicked on the big start button, and now we've come to our instrument setup page. So the first thing we would be doing when setting up a new test is priming our instrument. So what that means is that we're going to physically be equilibrating all the lines in the instrument with the running buffer for today's test. So to go through this process, we would click on this prime process start button. Once we open that up, it's going to tell us, please ensure that you have a blank chip present in the instrument to start this process. Now, in this case here, when we're coming out of storage or a long time of not using the instrument, we would probably have a blank chip in there. So the blank chip is just a piece of glass that has no gold on the surface. Now, if you are priming the instrument with a new buffer to run like a second or third test with the same sensor that you have in there, you can leave that sensor in the instrument for this portion of the setup. We would then click, so at this point here, sorry, I do have a blank chip already in the instrument, so I'm going to skip the undocking and docking step, but we will go through that when we set up the sensor in our sensor setup portion. So here we would then click next, and then we can input in the lines here what the buffer we have for each of bottle 1 and bottle 2. So like I said, today we're just running a simple diagnostic experiment. We're going to be using water as our running buffer. So I've chosen bottle 1 and written in there DI water. Now, I know we have water in bottle 3. In this situation, we're going to use bottle 1 with water just to simulate what it would feel like if we were doing an actual experiment. So once you have the description input in your selection there and it's selected, we would then click next. Now at this point here, it's going to take approximately 20 minutes to prime the instrument. I've already gone ahead and done this, so we're not going to spend that 20 minutes doing this now. But if you have to do this, I recommend doing it in the morning when you get into the lab. That way, as the instrument is priming, you can prepare your samples fresh, maybe you have a quick coffee break, and then come back to run your test. So once you've done that and the priming is completed, you would then see the status here switch to complete. Again, ours is started at complete because this was done previously. So once the instrument is primed, step 2 is going to be taking our optical references. So one might ask what that is. Well, we're going to be referencing out the spectrum of the light that we're detecting in the instrument. So because in our situation here, we're using an LED light source, this light is very stable for a very long time. The intensity doesn't falter for very quickly, so we don't have to take these references very often. And for that reason, we recommend taking them once a month. The reason we say once a month is just so you can see at the top here when the date has changed over to a new month, then it's okay, time to take a new reference. We want to do that just to make sure that the file is updated on the computer so that it hasn't been months or years since a reference has been taken. So we're going to go through how we would take a reference right now. So for that, we would click this Acquire New References button. And then again, the prompt with all of our instructions will come up on the screen. So in this situation, we need a clean blank chip to be loaded into the instrument. So again, that's just a blank piece of glass with no gold on there. At the moment here, we know that the instrument has that blank chip in there. So we again are going to skip these steps here, but don't worry, we will go through a full sensor loading in a few minutes. So now that we know the chip is docked, we're then going to click the next button and move on to the next step. So what's happening here is the flow cell is filling with our running buffer. So not only do we need a blank chip when we're taking our references, we want to make sure that there's solution flowing through the flow cell while we take these references also. The reason for this is that if the sensor spot is in air, then the air has a much larger refractive index difference than aqueous solution. So it'll cause our references to not be correct for when we're running our experiment. Now, another thing to note with respect to the references. Like I said, we want to take them once a month. Another time that a new reference would be necessary would be as if we change the LED light source. So for our 2-channel and our XT instrument, we have 2 different LED light sources. One's called the cool light, which is what's installed in the instrument when you get it. And it's a green LED board. And the other one is called the warm light. The warm light is a red board, and that comes in the accessories kit. Now, the reason we have 2 different types of LED light sources is because of our 2 different types of sensors that we have. We have our standard sensors and then our high sensitivity sensors. And the difference is the wavelength of light that the gold absorbs on each sensor. So for our standard sensors, the gold has a maximum absorption at 550, which is also where our cool light has its maximum emission at. And our warm sensors, or the high sensitivity LED light sources, high sensitivity sensors have a maximum emission at around 620. And that's where our LED light source, the warm one, has its maximum emission. All right, so at this point now, what it's telling us is to be inspecting the flow cell to make sure that there's running buffer present and that the bubbles are removed. So I'm going to show you how we would do this on the instrument here. So at this point here, we would then open up the lid of the OpenSPR, and we would be looking into the sensor stage area. So a quick overview of what we see inside the instrument here. Might be a little difficult with the camera position, but on the right-hand side here, this is our optical detector. So that's where the spectrometers are located, detecting the signal from our two channels, in this case, because it's a two-channel instrument. Beside it here is our sensor stage, which holds our sensor chip holder, so this little part that's sticking up here, which subsequently holds our sensor in place. This clear part here is called our flow cell. It's called the flow cell because that is where the liquid is flowing and interfacing with our sensor chip. And this little guy here is our LED light source. So it's tough to see here, but we have the green one in. If you need to change it, you would simply remove the screw in there, pull it out, put the warm light in, and then screw it back in. It's as simple as that. Now to check to make sure that we have flow, what we'd be doing is we'd be looking in through our sensor stage here. There's a little window cut out of the sensor holder where we can see if there's any bubbles and make sure that there's liquid flowing through the flow cell. At this point here, we see that there are no bubbles present. We have liquid in the flow cell, so we would go ahead and close our lid and move on to the next stage of our reference taking here. So at this point here, we'll click next. Again, we saw that there were no bubbles present. In the event that you did see a bubble, you would click on you would load 80% isopropanol into our sample loop and then click on the inject button, and it'll go through a bubble removal step. Now we're going to go through one of those once we get the sensor in here shortly, so that's the reason we skipped it right now. All right, so the optical references are in progress. What does that mean? Well, right now there's 4 spectra being taken. 2 are for our dark references and 2 are for our bright references. So in a few seconds, we will see those pop up on the screen here. So once it says optical references complete, we can then click OK. And we can see what our references look like in the background. So there are actually 4 spectra present here. There are 2 at the very bottom here. You can see the blue line for one of them. There's actually a red line behind there. So the red line and blue line denote channel 1 and channel 2. Those 2 spectra at the bottom are our dark references. For those, the LED light is turned off, and then a spectrum is acquired. And we see that it's a flat line for both channels because there is no light detected from our spectrometers when that LED light source is off. So that signifies also that there's no ambient light that the system can detect. The other 2 spectra we see here have a maximum at around 550. So as I said, for our cool light, we want to make sure that it has its maximum emission at around 550 because that's where our standard sensors absorb the light at. We can see that the rest of the spectra don't overlay quite well for both channel 1 and 2, and that's because we only care about between 500 and 600. That's where the LED light is calibrated for. The rest of the light spectrum there, we don't really care what the absorbance is at. So when taking these references, we want to ensure that every time we do this, this looks the exact same. If the reference looks different to you or odd for some reason, or you suspect that something's wrong, you can compare it to the operations manual, and your figure should look the same as what you see on the screen here. So it should have a maximum around 550 and a maximum intensity of 14,500. Now, some reasons why you might have a different looking spectrum. A, if you had left a gold sensor in the instrument by accident. So instead of taking our blank chip with no gold on it, you left the gold one in there. That's going to obviously have a different absorption spectrum, and the reference are going to look different. B, if there's no liquid in there, like I said, air has a much different refractive index than aqueous solution, and since our spectrometers are quite sensitive, we can detect that when we take our references. And lastly, if those 2 seem correct, if the blank chip is dirty. So if you have fingerprints on there because you were handling it without gloves, or it was dirty from sitting on your lab bench and you didn't clean it before you put it in, that could cause the references to be taken incorrectly. So at this point here, the priming is complete. Our references look ideal. We can then go to the top here and click Next. And what's going to happen is we see a new tab open up. This one is now called our Sensor Setup tab. So in here, what we're going to do is we're going to set up our sensor for the experiment we're going to be running. We can see in our channel 1 and channel 2, the absorbance is approximately 0 for both channels. That's because, again, we have a blank piece of glass in there with no gold on it, and we just took references. So even if something of there could have absorbed, we have now referenced that out. So to load our sensor, what we're going to do is we're going to click this load sensor button. A pop-up is going to come up here saying, do you want to remove the existing sensor? So our instrument can detect when the stage is in the docked or the undocked position. As the stage is in the docked position now, the instrument is telling us, well, it's in the docked position, so a sensor must be present. Do you want to exchange this for a new one? The answer is yes, we do. So we're going to click Load New Sensor. You're going to hear the sensor stage physically moving, so it's going to open up. And then what we're going to do is we're going to remove this sensor chip, and then we're going to clean the flow cell. So it should be second nature. Every time you go to undock the instrument, you should be wiping the flow cell with 80% isopropanol. So I'll show you what that looks like right now. So what we're going to do is we're going to open up our instrument. You can now see that our sensor stage is undocked, so it's closer to the optical detector. We can remove our sensor holder, which has our sensor chip in here. So this is what I'm talking about by a blank chip, literally just a piece of glass with no gold on it. So what we're going to do is we're going to take a Kim wipe, because we're going to keep this on the bench. We're going to use it later, and I'm just going to store it on the bench right now for later. Now what we need to do is we need to wipe that flow cell and wash it with our 80% isopropanol. So again, we'll take one of our lint-free wipes here. Again, if you don't have these, you can use a Kim wipe. We have our 80% isopropanol, and all we're going to do is we're going to add a little bit of it to our Kim wipe. Now, if you want to pipette it on there or anything of that nature, you can do that. Once your Kim wipe is wet, you're then going to just clean the flow cell by rubbing it up and down to remove any liquid or particulate matter that might be on there. Now, the reason why we want to do that is we want to make sure that the flow cell is completely clean and dry for when we go to dock our new sensor. So if we were using a running buffer right now, PBST, there would be some residual buffer on the surface, and if that were to dry up, we could have salt crystallize on there. When we go to dock our chip, they won't form a perfect seal, and we'll see leaking. So this removes any residual buffer, any residual gold from a previous sensor, and keeps it nice and clean. So what we're going to do now is we're going to move on to the next stage of our setup here. So we'll click again on this Load New Sensor button. And what it's going to give us the instructions for here now is how to prepare our sensor chip. So I'm going to go ahead and do this right now, and I'll let you see what that looks like. So again, we're going to take our diagnostic sensors. So in our container, a little difficult to see here, but our sensors are stored horizontally and 4 per row. In your diagnostic bottle, there are 4 in there, and there's 2 on the bottom row and 2 on the second row. You can see at the bottom here, the gold circle from our nanoparticles on our sensor. That is directly in the center of our container. So we want to be careful when we're taking it out. So to do that, we're going to again use our tweezers, have our gloves on. I like to take the lid off, have the label facing me, and then I'm going to stick the tweezers in to the left-hand side, grab the sensor about halfway down, and then pull it out of the container. So here we can see the sensor out of the container. If you feel comfortable, you can close the lid and move it to the side so you don't spill anything. Now what we need to do is we need to clean this. So here we're going to take our waste beaker, and we're going to take our squirt bottle of water. Again, if you're wearing gloves, you can handle the glass. I'm just going to rotate it so that it's vertical, so I have it sturdier in my tweezers. And we're just going to rinse 2 or 3 times on each side from top to bottom, avoiding touching the sensor spot so that we don't damage it at all. All right, so once it is clean, now the reason we want to clean it with water is that most of our sensors are stored in some sort of buffer. Again, when we dry it, we don't want that salt residue causing an imperfect seal on our instrument. Now, if you have compressed lab air or nitrogen gas, you can use that to dry your sensor. I have this little hand pump that I'm going to use, and basically we're just going to blow the liquid off. Now, the easier way to do that is having a Kim wipe present and then just blowing the water down so that the Kim wipe can wick the liquid away from the sensor surface. So depending on your skill with these hand pumps, mine is not the greatest at the moment. It could take you between 20 or 30 seconds to get this completely dry. And again, it's imperative that we get it completely dry. When the sensor chip is drying, you'll notice that the gold sensor will change colors. That indicates that it is now dried. As I said, with gloves, we can be holding this. If there is some liquid on the sides, you can take your Kim wipe just to wick that away, as long as you don't touch the sensor surface itself. So once our sensor is completely dry, again, I'll just take our tweezers here. we're then going to load it in our sensor holder. So if the holder opening is facing you, so the side where that interfaces with the flow cell, we want to make sure the sensor chip has that cut corner in the bottom right, because that's going to denote that the sensor is facing outwards towards us. And we want to slide it in there, and it'll slide down nice and gently. Now, one thing you'll notice on the sensor holder is, on the one side, there's a large notch cut out of it, and on the other side is a small notch. The sensor only fits in one orientation in the holder, and subsequently the holder only fits in one orientation in the instrument. This way the sensor cannot be loaded backwards. So once you have that loaded into the instrument, what we're going to do is then we're going to click the dock button. What you're going to see here is it's going to say, oh, attention, the lid is open. We have a safety feature built in where the lid has to be closed anytime we're using the dock or undock feature, so that no one can get their fingers pinched in the mechanical instrument there. So once the lid is closed, you can press OK. The instrument will dock the sensor for us. And again, this is all done remotely by the instrument, so it'll dock it to the same setting every time, so you don't have to worry about it being underdocked or overdocked. And then what we'll do now is we'll click the next button. Before we click the next button, I just want to point out one more feature here. We can see in the background that the absorbance is at around 500 right now. And as I said, the sensor has a maximum absorbance at 550. What we're looking at right now is the absorbance of the gold when it is dry. So the gold has different absorption properties, whether it's wet or dry, and depending on the aqueous solution that it's in. So if we click next here, the sensor is going to now fill with our running buffer. And what's going to happen is as that sensor fills with the running buffer, the gold is going to now get wet because it's submerged in the liquid. And we see that the spectrum has now shifted to around 550, signifying that the gold has been loaded correctly. Sorry, not the gold, but the sensor has been loaded correctly, because if it was backwards, the chip would not be able to get wet, and we wouldn't see this shift in absorbance. So this just takes a minute, because what it's doing is it's filling channel 1 first, and then it's going and filling channel 2, so it's shifting back and forth. And then after this is done, what we're going to do is that bubble removal step that we skipped earlier when we were doing our references, but we'll take care of that now. So for that to occur at this point here, we can actually open the lid on the OpenSPR. So I'm going to go ahead and do that while we wait. And the reason we're going to do that is that we want to physically be looking inside the instrument to see that there's liquid in the flow cell, to see if there's any bubbles present. So I typically, before I were to have clicked the fill button before, I would have the lid open so I can physically watch the liquid flow through the channels. So what it's telling us now is that the sensor was loaded successfully. We know that because we have a nice signal detected, and it's asking us to perform an inspection of the sensor area. So what that means is that we're going to physically look underneath this hard plastic piece here, and on top where the interface between the chip and the flow cell is. The reason we want to check those two locations is that if there was a leak present, that's where we would visibly be able to see it. At this point here, everything looks good. So next thing we're going to do is we're going to proceed to our bubble removal step. So to do that, we will just click next on this software here. And in this case here, even if we don't see any bubbles present by looking at the flow cell, we still want to do this step because we just opened up the instrument and closed it. So we have introduced air into those lines. So we want to make sure that we remove all the air now by injecting this 80% isopropanol. So I'll go ahead and show you how we would do that. So again, this is another reason why we have our 80% isopropanol here. I have one of my syringes with a blue blunt end tip on it. So we always want to make sure we use a blunt end tip so that we don't puncture the seal in the injection port here. And I have this syringe labeled as 80% IPA because again, I like to reuse these. You can even though they're disposable syringes, as long as we keep them from one type of solution, we can reuse them multiple times. So I know the software said we want to use 150 microliters. I'm going to go ahead and use 300 microliters. We want to use a little bit of excess of the isopropanol. It moves a little more quickly through the tube, so we want to make sure we're also not putting bubbles into the system by incorrectly loading the isopropanol. So to load the syringe, we're going to stick the blunt end tip into the bottle, and we're going to slowly pull the plunger up so that, again, we don't introduce any bubbles into the sample. And we'll pull it up to about the 0.3 milliliter mark. So what that looks like is this. You'll see an air bubble in the syringe. We need to keep that air bubble there. So here we see it's at the 0.3 milliliter mark, the plunger. The liquid is at the 0.2 milliliter mark, but there is 100 microliters in the tip itself. So we do have 300 microliters of liquid in there. And that bubble, we want to keep it on the plunger side so that it can push that liquid out of the instrument or out of the syringe. So what we're going to do now is we're going to put the blunt end tip into the injection port. Now you might find that you have to wiggle a little bit to get it in there, but you want to make sure that it goes all the way to the first stopping point. Once you get to that stopping point, you don't want to push it anymore. Again, there's a seal there. We don't want to puncture it. That blue blunt end tip of the syringe will be about 1 millimeter from the blue part of the injection port, and that's the correct distance that it should be inside there. So almost a whole 1 inch of the tip should be loaded. There's about 1 millimeter left that you can see of the metal part. Then we're going to slowly depress the syringe to load our liquid into the injection port. Now, I only load about 90% of this. So what I mean by that is you can see the plunger isn't all the way to the bottom. That's because we've loaded excess isopropanol. We don't want to push it all in case we put some of those bubbles in there. So you want to load about 90%, 95% of what's in the syringe. Once this is loaded, we can then go back to our software here. And then we're going to click the inject button. So again, at this point here, I would leave the lid open because we can see if there's any bubbles that are going through the instrument. If a bubble does pass, you'll also be able to see it in the spectrum. See how the spectrum shakes there? That's because a bubble has now passed through the sensor area. So some things to note here with when doing this. It is common to have to do this step 2 or 3 times when you put a new sensor in there. The reason for that is if there are some bubbles in the flow cell area, they will adhere to the gold that's on there. So it'll take a couple of these injections to remove the gold. Now, the reason why this isopropanol does a good job of that is it has a lower surface tension than the liquid that's in there, so it pushes it out and the air out through the instrument. So everything seems to be looking pretty good so far. This step does take 2 minutes and 10 seconds. The reason it takes that long is that we are doing 3 separate 10-second pulse injections of isopropanol. So what that means is that we're going through channel 1 and 2 with a 10-second pulse. Then we're flowing our running buffer through. So in this case, water. Then we're switching to channel 2, another 10-second pulse, flowing water through to remove that isopropanol. And then we switch back to channel 1, 2, and do that last pulse and flow liquid through. So that's why this is a little lengthy, but it's to ensure that we remove all of the bubbles from the instrument. So at this point here, again, I'm looking at that sensor holder, that little window in there, to make sure that there are no bubbles present in the instrument. Now, one thing to note, because we're going to get into that next when we start doing our proper sample injections, is for a proper sample injection, we always want to wash out the sample loop with our running buffer, then purge with air, and then load our sample. Some might ask, well, why didn't he do that right now when he did the isopropanol? That's because the isopropanol step today was the first step that was done on this instrument that was coming out of being shut down for a while. So I know that the sample loop was already cleaned and dried out. There was nothing in there. So that's why I could just straight on load our isopropanol. All right, so now we see this injection is complete. Again, we're going to do that inspection of the flow cell area. Great, we see that there are no bubbles present. So again, sorry, I'll show you what that looks like. So again, we're going to be looking in from the right-hand side into the window here to make sure there's no bubbles that are visible. If a bubble was present, it would be a pretty bright circle with a bit of a shadow around it. And then you would just need to click the repeat button here and then load some more isopropanol into the instrument. In our situation here, we don't need to do that, so we can click the finish button. So at this stage here, we see we have a nice healthy signal in both channel 1 and channel 2. And they're both around the same absorbance. If they don't get to the exact absolute same absorbance value, that's okay. There is a tolerance. Anywhere between 0.04 and 0.06 is acceptable. Here we're off by about 0.01, so we're looking pretty good. And then we see our step 4 here, the bubble step is complete. So what we're going to do now is we're actually going to start our experiment. To do that, we're going to close the lid. So at this point, we want to make sure we leave the lid closed. Then we're going to click the next button, and it's going to take us to our experimental data tab. So here we can put our test name in. So training. And then we see that this folder is going to be located on the computer under Documents, OpenSPR, and then Test Results. A folder has been created with today's date and the time we started and the name that we just gave it. So you don't have to add the date and time in here. It's automatically added to the folder. And now we'll click OK. So what we're going to see here is we're going to see our data streaming in real time. On the x-axis is our time in seconds. On the y-axis is our response, and our arbitrary units are RU for response units. Each RU corresponds to a change in absorbance of 1 picometer. So again, very, very sensitive. At the moment, we see that there's a slight drift in this in the baseline here. That's very common when you put a new sensor in. The sensor, again, I told you, is stored in a buffer in the container. Today we're using water, so it's going to take a little bit of time for the baseline to equilibrate. Other things we're going to look at here with respect to the software itself are on the top ribbon. So first thing here we have is finish. So this is the button we're going to press to finish the test. We'll go through that later. We're not going to do that right now. The next one is our temperature control. So the default temperature for the instrument is 20 degrees Celsius. We have the ability to go up to 40 degrees or down to 10 degrees below ambient. The reason we can only get down to, in this situation, 11 is due to the temperature and humidity in your room. So in the instrument, on the back mainboard, we have a temperature and humidity probe built into it to detect what that ambient temperature is so that we don't go below the dew point of the room. Otherwise, we would get condensation on the glass and the metal. The next box here is our ligand wizard. So if you're going to be starting a ligand immobilization, you can click on this wizard and choose the chemistry that you want to use for your test. And then it'll walk you through all the steps to clean the sensor, activate the sensor, load your ligand, and then depending on the chemistry, block the sensor also. In this case, we're not doing an immobilization today, so we can click cancel. Next thing here is our running buffer. So at the moment, we primed with bottle 1, which was our water. If we wanted to, say, immobilize our ligand with PBS buffer, but we realize that we need BSA in the running buffer to suppress any non-specific binding, we can then do the ligand immobilization and then do a buffer change after into the running buffer with BSA. Now, reasons why you might need to do that is, for instance, if you're working with a carboxyl sensor, our running buffer cannot have anything with a primary amine group in it. So BSA is a protein, has primary amines. Otherwise, during the immobilization step, it will covalently couple via amine coupling to the sensor surface. So once the ligand immobilization is done, we've finished with the wizard, we would then do a buffer change. Here we have the ability to change our flow rate. So we have a flow rate, we can go down to 5 microliters per minute, all the way up to 200. For our diagnostic test, we have to use a speed of 75 microliters per minute. Now, one thing with respect to the flow rates that we have, this allows us to have an interaction time of anywhere from 30 seconds, so at the highest flow rate, up to 20 minutes at the lowest flow rate. And that interaction time is determined by taking the sample loop volume. So in our case, our sample loop is 100 microliters per minute, and then dividing it by the flow rate. So 200 microliters per minute gives us 30 seconds interaction time, 5 microliters, 20-minute interaction time. The next box here is our injection box. So here's where we choose the channels we want to flow through. So right now we're going through both channel 1 and 2. And then we can click the inject button once we're ready to do an injection. So here's where we want to be careful with our terminology with respect to the use of the word load and the word inject. So when we're introducing our sample to the sample loop, we always refer to that as loading. So it's the same as if you were to use, say, an HPLC or an ACTA. We have a very similar valve with a sample loop. So when it's in the load position, our injection port is able, or is, I should say, able, it's fluidically connected to the sample loop. So when we push liquid through the injection port in the load position, that liquid will go in the injection port, through the valve, through the sample loop, and then into the sample waste tube. When we click the inject button, that valve is going to switch, and now that sample loop is going to be fluidically connected to the running buffer that is flowing through the instrument. So it's exactly the same as when you're loading your sample for purification on the ACTA. You load it into the sample loop in the load position, and then you inject it after it already is in the sample loop. So again, we won't be clicking this button until our sample is in the sample loop. The next thing here is our graph function. So here we can control the graph, or we can modify it in ways like we can switch the scale if we want. We can choose to auto scale, and then we can save the graph as a PNG. So you can also save a picture of what's going on your screen. Now, all the data that we are collecting is saved in real time, so you don't have to save a picture every time you do an injection. This feature is useful if, say, you're running a test, something looks quite odd after you've performed some operation on here, whether it's an injection, flow rate change, temperature change. We encourage you to take save a picture of that graph, and then you can email it to us at support@nicoyalife.com, and then we can help you diagnose anything that could be happening that is wrong with your instrument. Now you'll see this big 0 button here. I'll show you in a second. Now, other things we can do is we can actually manipulate the graph we're looking at now. So right now we're in what we term auto scale. So what's happening is that the graph is auto scaling as more data is being acquired or obtained. In the instrument, we are obtaining 10 data points per second. So we see 10 data points per second streaming on here with some averaging that makes the curves look a little smoother. We can move the graph around by holding the left click button and dragging the graphs anywhere we want. We can zoom into the graph by, if you're using the trackpad, holding the control button and then the left click and dragging a square across to the portion of the graph we want to zoom into. And we can do the same thing, and then we can also zoom in and out by pinching in and out with our fingers, much like you would do on your phone. You can do that for the whole screen, or we can do that just for one axis if we want to leave the response units untouched in one of the other axes. Now, if we want to go back to that auto scale, we click on this gear button in the graph box, and we then click auto scale. Another thing you'll see here is this corrected preview. So what that is that we can actually preview what our corrected signal looks like. So it's going to take this red curve for channel 1 and subtract it from the blue curve and then give us our corrected curve. So here we can see if we were to zoom in, the noise is on the order of 3 to 5 response units, so quite small in comparison to the responses we're going to be collecting during a test. Now the reason, so the fact that we have a noise level of 3 to 5 response units is the reason why, if you recall from previous conversations with us or the previous webinars, that Rmax equation, whenever we're trying to calculate for that ligand immobilization level, that's why we set the Rmax to 50, because we want it to be at least 10 times our largest noise value. Now, if we go back to our raw signals here and we click the 0 button, what's going to happen is our screen is going to be cleared. Now, as I said, all of our data is saved in real time. Nothing gets deleted. All that's happening is we've removed that first 475 seconds from our view, and now we're looking at all the new data that we're collecting. So this is beneficial for after we've done the ligand immobilization step. You might get a few thousand RUs of ligand immobilized. If your first analyte concentration is quite low and you're only seeing about 50 or 60 RUs, it's going to be quite challenging to see that if the scale is quite large. So that's why we recommend zeroing before then. And as you can see now, our baseline has stabilized quite a bit because it is equilibrated with the water that we're running during today's test. So some reasons why the baseline might be drifting during your experiment would be as if one of the main reasons, is if the buffer is not fresh. So we want to make sure we're making fresh buffer, we're filtering, degassing it. That way it is fresh for the whole test. All right, so another thing we looked up here is our pump features here. So we can stop the pump. When the pump is stopped, we can undock the sensor holder. You shouldn't have to use any of those. Typically that would happen if there was some error that was occurring and you're trying to fix it. Otherwise, you don't need to touch those because we will stop the pump when we're finishing the test or doing some operation that requires that. All right, so what we're going to do now is we're actually going to go ahead and do some sample injections. So I'm going to switch back over so you can see how I'm going to do this. So to do this, we want to follow our standard sample loading procedure. So what that means is that this is, in this situation, a 5-step procedure. Step 1 is cleaning the sample loop out with our running buffer. Step 2 is purging the sample loop with air. And step 3 is loading our sample into the sensor or sample loop. Step 4 is making sure we've chosen the right channels on the software, so we'll go through that later. And then step 5 is clicking the inject button. So again, we don't click inject until the sample has been loaded into the sample loop. So first step here we're going to do is we're going to clean this out with our running buffer. Today's running buffer is water. This is why we have another container of water aside here. And I also have a new syringe and blunt end tip. This one I've labeled as water because I'm going to keep using this for my water steps. So what we want to do is we want to wash the sample loop out with about half a syringe worth of liquid. So in this case here, I'm going to stick the syringe in. I'm going to pull it about halfway up. You can see I didn't do it as slowly as I did for the isopropanol. In this case here, if we have bubbles in the syringe, that's not a bother because we're going to be purging with air. So you can see here it's about halfway full. Doesn't have to be exact. And then we'll put the blunt end tip into the injection port. Again, might have to wiggle it a bit to get all the way in. Make sure it gets to that first stopping level. And then we're going to push all that liquid through. Again, here I'm doing it a little quicker because we're just washing out the sample loop. This is going to wash out any residual sample from our previous injection. So in this case, we had some residual 80% isopropanol in there. This is going to wash that out. So step 2 now is going to be purging with air. So we're going to take that same running buffer syringe, again, today's the water syringe, and we're going to pull the plunger down, and we're just going to physically load it fully with air. So there's 1 ml of air in here. We're going to stick the needle back into the injection port, all the way to that stopping section, and then we're going to push that air through. To be confident that you know that air is pushed through the sample loop and emptied it, you can look at the sample waistline going into your waste bottle, and you'll see air bubbles in there. The reason we want to push air through here is so that we don't have any sample mixing when we add the sample we're going to be injecting into the instrument. So step 3 now is going to be loading our sample, in this case our glucose. So I have another syringe, new blunt end tip, labeled for glucose. We're going to use that for this. We have our 25 milligrams per milliliter sample of glucose here. And for this one, I'm going to pretend this is one of our ligand or analytes, and we only have 200 microliters available. So we're only going to load 200 microliters into our syringe and sample loop. So to do that, we're going to stick the blunt end tip into the bottle. I like to keep the gradients towards me so I can see what level we're at. And this time again, we're going to slowly pull the syringe up until we get to the 0.2 milliliter mark. So it's going to look like this. The syringe plunger is at 0.2 milliliters. There's about 100 microliters of air in there, but that's because our needle has 100 microliters in it. So now we have our 200 microliters loaded into our syringe, and we want to make sure we leave that bubble in there so we can get the liquid out of the tip. So again, we'll gently put it into our injection port. Push it all the way to that first stopping point, not any further. We'll hold it there sturdy, and then we'll slowly depress the syringe to load our sample into the loop. Again, at this point here, I've loaded about 95%. I didn't push the syringe all the way down just to prevent any of that air from getting loaded into the sample loop. So we'll close our vials up here so we don't spill anything. All right, so at this point here now, our sample is loaded in the sample loop. And now we can go on to step 4, which is the channel selection. So here we're going to choose channel 1 and 2. So I want this to go through both channels. Once that's selected, we'll click the inject button. And what's going to happen is a pop-up is going to come here, and it's going to let us know or tell us to put our injection details here. So the name for the sample is glucose. We can go to the next line. Concentration is 25. And then from the drop-down menu, we can choose our units. So we have all the common units that might be necessary here. This one is milligrams per milliliter, so we'll choose the bottom units. Once we have that entered, we'll click OK. So one can see there's no rush to get those details in because the data gets appended to the beginning of our injection. So on the screen here, this solid black line is where the injection was started. So that's where the liquid is now flowing over the sensor area and interacting with our sensor surface. So what do we see going on here? What we're looking at right now is what we call a bulk shift. The sample we're using, this glucose, does not interact with our sensor surface. We have an inert sensor surface for our diagnostic sensor. The glucose does not interact with it, but it is giving it a different refractive index. So for the first 820 seconds, we had water going over the sensor. That has a particular refractive index. And then once we do the glucose injection, that has a different refractive index, which is why the response shifts up quite quickly and then plateaus. And then once the injection is complete, that response comes back down to baseline. So this is a textbook bulk shift. So this is something we want to avoid when we're doing our analyte samples because it gives us what we call a false positive response. Now, thankfully, with this 2-channel instrument, because we have this channel 1 as our reference channel, if you have a small bulk shift, we can correct for that. But as we saw in the previous webinars and with other data, if you've ever contacted us, if that bulk shift is a pretty high percentage of the overall specific channel in channel 2, the correction doesn't come out as smooth because we are removing a lot of what we thought was a positive signal from that response. So what we see here after the response is done, which is denoted by this dashed line, the response comes back down to baseline, suggesting that all the glucose has passed through the instrument. So what we use these glucose injections for, or if you don't have glucose, you can do 2% glycerol in water. We use them to diagnose the state of the instrument. So it'll help us diagnose the speed, the sensitivity in both channels, and if there's any other inherent issues going on. So for that experiment, we would typically do 3 of these in channel 1 and 2 injections, and then we would switch to channel 2. So what we're going to do is we're going to set up another injection right now. So you're going to be able to watch me do that again. We're going to take our water syringe. So step 1, we're going to wash the flow cell with our running buffer, which is water today. So again, we'll load it halfway up. Don't care about the speed or how exact it is in there. Just half a syringe full of our running buffer, today water. And we'll put it into the injection port. And we're going to load that liquid, and it's going to flow through the sample loop, it's going to flow through the sample loop into the sample waste tube into the waste bottle. And that's going to clean out any residual glucose that might be in the sample loop. Next, take the same syringe, fill it with air, and then we're going to put that in there to purge this liquid out so that the sample loop is empty and devoid of liquid. This way, it can't mix with the sample we're going to be loading. And now we're going to take our glucose. Again, we'll use our glucose syringe. So that's why I like to label my syringes so I don't contaminate anything or confuse them. And then again, we're going to stick the blunt end tip into the solution, and we're going to slowly pull the plunger up so we don't introduce any more air bubbles. And we'll take it to just above the 0.2 milliliter mark. So again, to be clear, we're just above the 0.2 milliliter mark with the black plunger. The liquid is at about the 0.1 milliliter mark. There's 100 microliters of liquid in the tip. So we need that air bubble to push that liquid out. And then we'll gently put the needle into the injection port, and we'll slowly depress the syringe to load our liquid into the sample loop. So now the liquid is loaded. Again, we wait a couple of seconds to let the pressure equilibrate before we take the needle out. Otherwise, we might get backflow. And we'll close up the vials again. Okay, so now we're going to switch back to our software. And for this one, what we're going to do is we're going to switch to channel 2. So what that means is now we're only going to have liquid flowing through channel 2. Oh, I'll address that comment that just came up in a second. Oh, also, I forgot to mention, if you do have any questions about what is going on right now, feel free to message in the chat, and I will get to them as we go through this webinar. So now that we've changed to channel 2, and the sample is loaded, we will then click the inject button. Again, we'll put our sample details here. So we'll put glucose. I'll put this for number 2. Concentration is 25. In our drop-down menu, we will choose milligrams per milliliter. And then we will click OK. So again, we see our injection line here. This is the sharp, straight black line with our sample details appended to before it. And we can see what looks different now is that the response is only coming through channel 2. We've selected channel 2 only. Channel 1 is now cut off. No liquid is going through channel 1, and we're only seeing the response in channel 2. So for this type of injection, you would only choose channel 2 at the times when you're running your ligand injection, because we only want the ligand to mobilize into channel 2. Channel 1, we don't want any ligand. We're going to block that with a blocking molecule after. So a couple other things I haven't mentioned yet at the top here is some of our timers that we use when running an experiment. So the first one is time since last injection. So as soon as that inject button has been clicked, this timer starts counting up from 0. This injection remaining timer will start counting down when that injection timer is hit. And when it gets to 0, it'll switch the valve back to the load position and cut that injection off. Now, one thing to note with this time since last injection, If you're doing, say, some analyte injections of a system that has a high affinity or just even a slow off rate, you're going to probably need to have, a comfortable amount of dissociation time to calculate an accurate off rate. So say you have, 6, 8, 10 minutes of dissociation. So if you have, 2 minutes of association, 8 minutes of dissociation, this time since last injection will reach 10 minutes before you get to a regeneration step. You want to make sure that for all of your analytes injections, you use the same timer here. So I'll address the one channel, like the old one channel, and the XT software differences in a few seconds once we finish with this last injection here. So one thing we can see now is we can look at our corrected preview, and we'll see that for the first injection, the line is 0. There's a few, these spikes here are due to the correction because this is just a preview. And also, like I said, when the channel 1 response is as high as the channel 2 response, it's very difficult to get a clean subtraction just because of the offsets and the timing. And we see for our second injection, we have our full response because only channel 2 saw the sample come through there. So we would use this corrected preview when we're looking at our analyte responses. So this is going to subtract any bulk shift or nonspecific binding that might be present. Now, again, if you are running this as a diagnostic test, we would recommend doing 3 injections of each. So 3 through channel 1, 2, 3 through channel 2, and then you would send that data over to us to analyze it to ensure that the instrument is running correctly. This is also a great protocol to run for training a new student in the lab. You can feel free to access this video at any time after we're done here. It'll be on our YouTube page. Okay, so now some differences between this and our other instruments. So for instance, with the XT instrument, we don't have these controls up top here. Those controls are visible, but we are unable to control them because we have to set up the test timeline before the test starts because it's all automated in the auto sampler. So what that means is that there's actually going to be a few more tabs at the top here before we get to this experimental data page. You'll see one that says baseline preview. So it'll show us what the baseline looks like again, because it takes time to equilibrate. If you're changing the temperature, you would do it then so that it can equilibrate before the test starts. Then you would have your sample setup page where you're going to tell the instrument which wells your sample are in. You'll have your test timeline page, which is going to tell the software what operations you want to do. So do you want to run a ligand wizard for what chemistry? Do you want to run a regeneration step, blocking step, analyte? How long do we want to run it for? 300-second interaction time, 150-second interaction time. Do you want it to go through channel 1 and channel 2 or just channel 2? And then, any process changes like you want to do a buffer change, temperature change, that would all get built into the timeline. And then when you get to this experimental data page, it's going to execute all of those commands you gave it. When you're on this page in the XT, you will still have the ability to finish the test. You'll also have the ability to pause and stop it if you wanted to. Now, with respect to the old SPR system, so our original one channel, what we would call some would have been have heard it described as the Rev 3. That one uses a similar software interface as this. However, we don't have 2 channels. We only have 1 channel. So what that means is that we can only inject the liquid through 1 channel on the flow cell. So the biggest difference is the flow cell itself. In this instrument here, the flow cell has 2 channels, so liquid can go through 2 different parts of a sensor. The old instrument only has 1 channel. So what that means is that we can't have real-time referencing like we do here. We would have to run 2 separate tests when we're running an experiment. We would have to run a control test. So what that would be is a non-specific binding test that allows us to check if there's any bulk shifts or non-specific binding. And then we would run our specific test where we've made any necessary adjustments to our running buffer, added some additives that we might need to combat that non-specific binding, making sure that the running buffer is the exact same as the analyte sample buffer, so there's no bulk shifts, and then we would collect that data. But as for the ribbon diagram up top, there's a lot of the same elements, except we don't have, that one also doesn't have temperature control. So you'd be able to finish your test. You would be able to stop and pause the actual pump. And then when the pump is stopped, you can put the tube into a different buffer to do a buffer change. You can change the flow rate. In that one, the flow rate goes from 20 to 150. So our new instrument here has an expanded flow rate range. And again, there'd be no different channels, so you can only click the inject button, and you have the same graph features. So you have the auto scale, take pictures, the zeroing, and then here you'd also be able to stop the pump and change the sensor. So there's only 1 screen on the old instrument because we don't have the automated docking system here, you'd have to manually put the sensor in and out. And this is a different, so that has its own different software. So all this software is located on our website. You would just have to choose the correct one. And again, when we do have software updates, we do send emails out to you to let you know that there's a new software available. So does that answer your question? And also at this point, do we have any other questions before I finish up this test here? All right, as I wait for more questions to come in, I'm going to finish this up and show you what we would do next after we've done this. So what we would do is we'd click the Finish Test button. It's going to ask us, are we sure we want to finish? Yes, we are sure. And now what's going to happen is it's going to create our data files. So what it's creating right now is our traceDrawer files. So as I said, the data is all saved in real time. The data is saved, though, as an Excel file, and then when the test is complete, it converts that into all the traceDrawer files we might need to analyze our data later in traceDrawer. Next, it's going to give us 4 options as to how we want to proceed. So option 1 is, do we want to start a new experiment with the same sensor? So what that would be useful for is, say you want to use the exact same ligand, you're testing out a different analyte or a different buffer condition. You can end the test after the first 5 concentrations of analyte 1 are done. Start a new test with the same sensor. That way you can have a different data folder with all the data that you've accumulated in a nice and tidy for when you're looking at it later. Option 2, start a new experiment with a new sensor. So that'll take us back to the sensor setup page, and we can change the sensor, start a new experiment. We don't have to prime again. We don't have to take references. That's already done. We just want to change the sensor to use a new one. Third one is place the instrument at the standby mode. So standby mode is recommended if you're not going to be using the instrument for a few days or a week or 2. I'll go through standby mode in a second because we're going to be putting that into standby mode now. And the last one is shutting down the instrument. So the shutdown is recommended if you're not going to use the instrument for a few weeks, or you're not going to be using it for a few weeks, a month or 2. So it's going to go through a full shutdown procedure. There's 3 operations there. Each step just requires you changing the tubes into a different cleaning solution, but there is a 30-minute wash between each step. So it takes an hour and a half, but you only have to click the button once every 30 minutes. So whether you come back in exactly 30 minutes or 50 minutes, an hour, it doesn't matter. Just has to let it wash for that 30 minutes. All right, so what we're going to do now is place the instrument in the standby mode. So if you do that, we'll click Next. It's going to ask us, do we want to change the sensor? At this point, yes, we're going to click Yes. We recommend changing it to that blank piece of glass, unless you're going to be using the sensor that's in there again for another test. So for instance, if you have a carboxyl sensor in there with your ligand immobilized to it, coupled to it, say you ran a test in the afternoon and you want to run another one tomorrow morning, or say you ran one in the morning, you want to run one after lunch, you could put it in standby mode in the running buffer from that test, come back that afternoon or the next day, start a test with that running buffer with the same sensor in there. In this case, we're not going to be reusing the sensor. We're going to shut this down for the rest of the day. So we're going to put that blank chip in. So here we're going to click Yes. And now it's going to say, follow the instructions below to go into standby mode. So again, the instructions pop up for every stage of the test setup and finish. So here we're going to undock. So we're going to hear the instrument undocking as the sensor gets removed. And we're going to put that blank chip back in there. So I'm going to show you what this looks like as we do it together here. So we're going to open the lid. Our stage is undocked. We can take our sensor holder out. Now what we're going to see is that some of the gold has come off the chip. That's completely normal because our sensors are manufactured oversized so that they encompass both channels on the instrument. This is another reason why we need to clean with the isopropanol wipe to remove any gold that's on the flow cell. You'll notice that there's going to be at least 2 channels on your chip because that does not come off because that's where the liquid's flowing through. It has nothing to touch. Nothing can strip it off the surface. So for now, we're done with this chip. I'm going to put it aside and dispose of it later. And we're going to get ready to put our blank chip back in. So first rule when undocking, we always want to wash with our isopropanol wipe. So we're going to take our Kim wipe here. We're going to take our 80% isopropanol. We're going to wet it, and then we're going to gently rub up and down. Now, again, you want to make sure you clean it thoroughly because some of the gold is on the flow cell. So we just want to make sure that gets removed. And once we're confident that it's been removed, we're going to then take the blank chip that we put aside earlier. So again, it's just the piece with no gold on it. And we're going to take that same wet wipe, and we're going to make sure we just wipe off if there's any dust that's settled on here during the test, any residual liquid, because we had it running with running buffer before, if that dried on here, we want to make sure it comes off. Again, we're going to have our sensor opening facing towards us, cut corner in the bottom right, tough to see there, and we're just going to slide it gently into the sensor holder so it'll fall right to the bottom. If you were to put the sensor chip backwards, you'll notice that it doesn't go all the way to the bottom. That tells you that it's backwards. So again, cut corner in the bottom right, it'll slide all the way to the bottom, and then we can just drop it into the instrument and we'll close the door. So now we can go back to our software here. We'll click the dock button. You'll hear the instrument moving the stage and docking it, and then it is now complete. So again, we followed all these instructions here. We see the cut corner in the bottom right, our blank chip, no gold on the chip. We then click next, and it tells us what buffer we want to use. So this is going into full shutdown mode for a while, or standby mode for a little while. I'm going to choose DI Water 3. But like I said, if you finish the test on a sensor you want to use again this afternoon or tomorrow morning, you can leave it in your bottle one with the running buffer that you finished the test with and leave it in standby mode in there. That way, the protein on the surface is happy. It's in the proper conditions that it needs to be. Once we've chosen the bottle we want, we then click next. And in our case, since we are doing a buffer change to water, it's going to do that 21-minute buffer change, and then it'll be in standby mode. All you'd have to do is click OK after that, and it'll say at the bottom left here, in standby mode since whatever date you put it into standby mode. All right, so I hope that was informative. That is one of our remote trainings, and also coupled with the diagnostic test that we would run if we were diagnosing any issues on the instrument. If you have any questions, again, feel free to write in the chat right now. If you don't have any questions, but have some at a later time, feel free to email us. Again, that's support@nicoyalife.com. This video is going to be available on our YouTube channel. So if you're using the instrument for the first time, or it's been quite a while since you've used it, or you're training new students or lab members on it, feel free to use this as a training material for that purpose. All right, well, doesn't appear to be any questions at the moment, so I hope you've enjoyed, and we will talk to you soon. I hope everyone stays safe and have a good rest of your afternoon.